In this video, we will study the atomic model proposed by Niels Bohr, the first quantum mechanics-based atomic model. The atomic models were studied since ancient times, as a necessity to describe the very fundamental nature of matter. Several models were accepted, but we focus only in those proposed during the modern physics revolution. The first of them was the model proposed by Rutherford after his results on shutting alpha particles at thin gold foil. In particular, in his model, Rutherford proposed a solar system-like model, where the electrons were moving around the atomic nucleus in circular paths. The issue with this model was the fact that any electric charge that experiences accelerations will radiate light. As a consequence, the electron should lose its energy and fall into the nucleus. This should result in an unstable atom that could only exist for a small fraction of a second. In order to solve this issue, Niels Bohr proposed a model for the hydrogen atom in 1913. This model was based on three postulates. Postulate 1. The negative electron moves around the positive nucleus in a circular orbit. All electron orbits are centered at the nucleus. Not all classically possible orbits are available to an electron bound to the nucleus. This means that the electron can only jump between the so-called allowed orbitals. There is no option to transition in between these spaces. Postulate 2. The allowed electron orbits satisfy the first quantization condition. In the nth orbit, the angular momentum L(n) of the electron can take only discrete values, as follows. With h bar, the reduced Planck's constant with this value. The quantized angular momentum will be studied in a future video. Postulate 3. An electron is allowed to make transitions only when the difference between the initial and final orbit energies is equal to the product h, f, either up or down. This means that the transitions are quantized and only allowed for the amount of energy absorbed or emitted. The most important prediction of this model is the following. When an atom absorbs a photon, the electron makes a transition to a higher energy orbit. And when an atom emits a photon, the electron transits to a lower energy orbit. This interpretation provided a good explanation to the discrete spectra. Let's focus on this interpretation. In the case of absorption, we can see that the electron takes the incoming photon and jumps to a higher orbit. The size of the jump is the same as the energy carried by the photon. On the other hand, the emission happens when the electron returns to its stable lower orbital. In such a case, the returning process generates a release of energy excess of the same amount of the energy distance between the orbitals. Due to the quantization of the orbital energies, the absorption and emission result in a set of discrete spectral lines, as discussed in the previous video. The Bohr's model also predicted the radius of the electron quantized orbitals. Let's calculate this radius. If we use the classical definition of the angular momentum and the second postulate, we get the following equation. Using some algebra, it can be seen that the orbital radius has this form. We can see that most of the terms in this equation are constants. We can call this the Bohr radius, that represent the distance between the nucleus and the electron in the hydrogen atom, when the electron is in its lowest orbital. Actually, the Bohr radius has the following value. Then, the electron orbital radius is the following. The Bohr's model also allows the calculation of the energy of each of the electron orbitals in the following way. The total energy of the any orbit can be found by using the following expression, where K and U are the kinetic and the electrostatic potential energies respectively. With some algebraic manipulation, the total energy is the following. Again, several terms in this equation are constants. When calculated the value of this constant, we get minus 13.6 electron volts. This is an important value, and it is called the ground state energy of the hydrogen atom. Finally, the energy of any electron orbital in the hydrogen atom is the following. In this equation, n is an integer greater than 1. Also, we call n the quantum number. It is important to notice that even when we have called E0, the ground state, it represents the case for n equal to 1. This is a convention and should be clear to avoid confusions. It is clear that there is an infinite amount of energy states, though the distance between states will decrease to very fast due to the dependence on the reciprocal of the square of the quantum number. Let's solve an example to understand how to calculate the energy of any orbital. Example 14. Calculate the energy of the first 3 excited states of the hydrogen atom. Express your answer in electron volts. Could you solve it? Answer. We know that the general equation for the calculation of the energy of any orbital is the following. As we need the first 3 excited states, then we use the values of n as follows. Then, the calculated values of the excited states are the following. If we calculate the wavelengths that correspond to these excited states, we see the following. We see that the calculated transitions range from the ultraviolet to the near-infrared, reproducing some of the results studied in the previous video. Finally, we need to understand that even when the Bohr's atomic model reproduced some of the phenomena that the classical physics could not explain, it is a limited model. In future videos, we will see how the quantum mechanics provided a better explanation for every single phenomenon present in nature. Stay tuned.